Greetings. Welcome to another edition of Insight Project. So I'm implementing the circuit I showed in the last video, and it's not a foobar. It's sort of a snafu though. See, that cap is actually 50 microfarads, not 10, and there's a lot of not unexplainable but different behavior with the setup like this. So what I mean, I remember a line from a Hollywood movie about a whoopee cushion. It's a Minkman. So, sorry. It's a Minkman. No, it's actually very good. And so we got this. We're cruising along at 1500 RPMs, 4-inch rotor, and this is just random. I just wanted to get the thing running, and it took me a while because I had to change out the cap. So that's 0.04 amps and 14.2 volts. We can also just kind of fiddle around here. You hear it? This thing gets scary fast. But, and this is not what you would see with the normal setup. I mean, geez, we're drawing like, what are we drawing like? I had to take it out of there because it just keeps accelerating. We were drawing like close to 2 milliwatts or something. I'll put it in there for a little while longer. But we'll look at this both in terms of how it does in and out of what I'm calling in and out of resonance, in terms of what we're using here. And I'll also explain why this is changing the way it does. But this thing gets scary. It keeps going. And so I can probably get away with smaller cap, but this thing's starting to scare me. That's 3,000, maybe 4,000 RPMs we're going to come up on. So let's put it back here. Why don't we? All right, now let's get down to it and really look at the thing. Okay, so this thing is a bit of an odd cat, and let's just talk through it and we can understand why it's behaving the way it does, and then we'll throw it out of resonance and it should be a lot less efficient. We'll put it back in resonance and you can see that it's actually very efficient. But what's going on here? Why does it have trouble starting up and then it gets going faster and it just wants to go faster and faster? So I talked through some of this on the last video when I was talking about making the circuit, but let's just sort of recap. Here you have a reed switch, and a reed switch is just, there's 2 leaves of iron in an evacuated glass tube, and when a magnet comes past, they pull together, and so now you have a connection. I think you can actually hear it. And so if you wanted to, I mean, it's a very clean connection, and because it's a small reed switch, it's very fast. If you wanted to, you could, with a monopole motor, you could just run it right from the reed switch. Just when the reed switch comes by, boom, you power the cap at the right place. However, if you want to do bipolar commutation like we're doing here, and if you want to time the pulse, which we're also doing here, as I explained in the last video. So if this is sitting here for a second, you still just get a 1 millisecond pulse. We're around there. And the way you use this reed switch across a voltage divider going to the ADC, you know, the ADC port on the Arduino, I explained in the last video, and I also made a video on making this thing. So this is sensing when a magnet comes past, and then it's doing something more complicated than just pulsing. It's either charging this in one direction or another, and it's only charging it for a set amount of time. So besides being a pulse motor, how is this different than a conventional sort of setup? So let's just say you had this, let's just say it's monopole whatever, and you had it where it's coming past, it trips the reed switch, and then the reed switch shuts off. And when the reed switch is on, for all that time, current flows in. So this would be a lot like a regular DC motor, except for it wouldn't necessarily be monopole. So let's say you're going so slow that it has 1 second where current's flowing in, and then 1 second off, and then 1 second in. So for that second, power flows in. Initially, there's a lot of reactive resistance from the inductance of the coil, and then as it charges up, there's no more magnetic field to increase, and so eventually you're left, let's say, it would probably be at like 1/10 of a second, but let's say at like 1/2 a second, the coil is fully saturated with its magnetic field. Now the only thing stopping the current flowing is the resistance of the DC line. And you see this like with a hobby motor. If you just put your fingers and stop the thing, you see the amp draw go, and you leave it there, and the thing will probably like melt or something. So staying with the conventional kind of setup, so it's like 1 second on, and the magnetic field just keeps getting stronger and stronger until it gets as strong as this electromagnet can put out. And as long as it can move, then it goes, 1 second off, and then that happens again, and it picks up speed. And now it'll be, say, a 1/10 second on and a 1/10 second off. So your duty cycle is still 50%. However, now, because it's only going for a 1/10 of a second, it does run into the reactance of the coil. The coil doesn't fully saturate, so it pulls with a little less torque, and it doesn't put as much current through because it starts to clamp down. Now it spins faster, and let's say 1/100th or 1/1000th of a second, it comes past, and then it's 1/1000th of a second off because it's spinning real fast. But the duty cycle is always 50%, whether you are at 1 second on, 1 second off, 1,000th of a second on, 1,000th of a second off. However, at 1 millisecond on, the dynamic resistance of the coil over that millisecond is going to be orders of magnitude greater than the straight line DC resistance. And so the amp draw is going way down because it can't push it through the reactance of the coil. The torque is also going down, and the motor is spinning faster. And that's what you see with the conventional sort of setup, conventional pulse motor, or just a conventional DC motor. So as it spins faster, the amp draw goes down, but the torque goes down. Slow it down, amp draw goes up. So like if you load a motor, you see the amp draw goes up. Now that's not what's happening here, because we've like forced it. We forced the issue. So with this one, when it comes past, it triggers for 1.5 milliseconds, how I have it set up here. We can change that, and we will change it. 1.5 milliseconds. And then it's off. So really, if you just like try and do that with this, sometimes it doesn't even have enough torque to get it to the next magnet. So I was thinking this is a disaster. However, if you give it a little spin, you see now it goes on for 1.5 milliseconds, and instead of being off for a second, it's off for a half a second. So in other words, the duty cycle is changing the faster it gets. And the faster it goes, the duty cycle increases and increases and increases. And so it just wants to go faster and faster because the duty cycle keeps increasing until either A, it's going as fast as it can for the friction here and whatnot, or it starts to step on its toes in terms of what it's doing in terms of turning on and turning off. So in other words, with this one, the pulse time is set. And so, if you have 1,000th of a second on, and it's going to take a second to get there, you know, your duty cycle is 1 in 1,000, and it might not even make it there. But you give it a little spin, 1 in 100, and then pretty soon it's 1 in 50, and then 1 in 10, and then it wants to just keep going faster and faster. But likewise, because the duty cycle is increasing, we see opposite to a conventional one, the amp draw keeps going up as you see the rotational speed increase, which is not what you see with a conventional motor. Now, why in tarnation did I do that? That's because, and this is a 50 microfarad cap, and if you set the timing to about there, then this cap just doesn't go to 0. It goes to, this one's only going to go to like -6 or 7. A smaller cap, you know, -8 or something like that. And so because it's bipolar commutation, and you went from 10 to -6, now you just need to add 4. So what I'm going to do is I'm going to change this timing now to where this thing only discharges to 0. And this would be like if you were just pulsing it through a battery. I mean, it's just the cap discharging to 0. We'll see the same sort of behavior as we saw previously, but it's going to draw a heck of a lot more power, and it's not going to spin any faster. At least that's my hypothesis. I haven't done it yet. And the other thing I'm very concerned about is that this is going to blow up because to try to explain this, when this thing has gone to 0, the cap has gone, I'm sorry, when the cap has gone to 0, the inductor has gone to its maximal field strength. If you just cut it off right there, then it's kind of like you've cut the suspenders, and you know, it's sort of a silly analogy, but it's just, you know, it's just naked now. It's pants have dropped, and it has all this inductance that it's shooting out. You know, call it what you want, a radiant spike, an inductive spike, whatever, and it's got no place to go. So it's looking for any capacitance to go and hide in, and it'll see the capacitance in your MOSFETs and things like that. And because the capacitance is so small, even if you're at 10 volts, it could be like a 500 volt spike, although it'll be very brief and weak, hopefully at 10 volts. But if I go up to 20 volts, it'll probably just fry these things because there's no place for it to go. Now, if I have it at the timing I have here, where the coil goes to its maximal field strength, this goes to 0, then we leave it on, the coil discharges, all of the field discharges, this goes as negative as possible, and then shut it off, there's nothing in here. So you don't have to worry about it because everything got shunted back to here. Okay? So what I'm going to try and do now is hopefully I can get away with 10 volts, and hopefully at 10 volts the inductive spike doesn't fry this circuit. Yeah, it's a reasonable hope. And we're going to change this to where the cap just discharges entirely. It doesn't go negative. And so that would be like if you were pulsing it from a battery. You know, it's just the cap is just discharging to 0. And what we'll see is, I haven't done it yet, but what I would say is, what I suspect we'll see is it'll spin fine, and the amp draw should be 2, 3, 4 times as much as when you interrupt it after the cap's gone negative. So let's do that now, and hopefully things won't blow up. Okay, I finally got it running with the 10 UF cap, and let me just sort of end with what this cap can do. And so we're at 20 volts, we're drawing that many amps, and it's spinning like this. Now this is where the cap, the cap is going fully negative, and then you charge it, and then it bounces back positive, and then you charge it. I've run it where it just discharges. It's harder to get it spinning, and it draws a lot more amps. I wanted to do a lot, like look at it very precisely and technically. It's hard to, because it's hard to get it spinning. But this is sort of what it does. But wait for it. Okay, now we're up to 200 milliwatts. Now you see, the faster it goes, because the pulse is a set time, the duty cycle is becoming shorter and shorter, and the torque is becoming more and more. And so, you know, it's not actually a dud. It's just like what you want to do with it. Stay with it. We're still at 200 milliwatts. See, it's even accelerating a bit quicker now. Again, the duty cycle is becoming shorter and shorter. I don't want to cut it off because this is too exciting. Sorry. We're at 200 milliwatts. We're spinning at, let me see if I can show it. I'll probably get, what's going on? All right. We're at 1660 and climbing. And now we're at 400 milliwatts. So it's actually not too shabby. Now it's got a lot more torque at this speed too. All right, now we're like well over 2,000 RPMs. 2,100. Don't do that. It's climbing. And yeah, I mean, all right, we're at 600 milliwatts. And what's different is that the faster this goes, the more torque it gets. So unlike a normal magnetic motor, electric motor, you know, it would get less torque as it spins faster. Because you already set at the beginning the pulse time, it's getting more and more torque the faster it's spinning. And it's spinning pretty fast for 600 milliwatts. All right, I mean, those magnets are all screwed in, so I'm not worried unless it's going like 10,000. I shouldn't say that, but it's going pretty well now. Up to we're closing in on a watt of power, and it's got some torque to it. But you know, it's back arsewards, because the more you slow it down, it loses more and more torque. So that's not good. But it's a fun, interesting motor. I gotta do one more thing. Yeah, I'm trying to get it to run, you know, sideways, 04 style. It doesn't have enough oomph in the cap for it. So, you know, sort of in closing, it's not a real impressive motor at the start, but I mean, there's a lot you could do with it. And that's not a big cap, but it's flipping back and forth, you know, 80% negative, then 80% positive. So that's why it's doing that right now. And you got to give it time, and then you got to realize that the faster it goes, because there's only a set pulse of, say, a millisecond, the duty cycle is becoming shorter and shorter, and so it's actually becoming more torquey the faster it goes, the exact opposite of a normal magnetic motor. Wait for it. Wait for it. That's where we're still at. Wait for it. So that's what we're at now. Wait for it. So that's what we're at now. So that's probably getting about to it. That's probably about it. So we're at like a couple thousand RPMs for less than a watt. And it's getting more torquey the faster it goes. Let's turn it up to like 25, 30. Alright, this is crazy. You can hear how it's accelerating now. Because now it's got torque. It didn't because the duty cycle was too slow early on. Now listen to it. It's got some get up to its giddy up. Holy shit. It's like 4,000, I bet. I don't want this thing to blow apart. My gosh, we're closing in on 3 watts. That's enough. That's enough. Alright, so in summary, I mean, it was a goofy idea, but it worked. It's just you have to understand what's going on with the torque and whatnot with a machine like this. But you can recapture a lot of the energy. And that's what I showed because that was so low when we were doing it. Otherwise it wouldn't have been that low. Alright, thanks y'all.